Hello folks, today's topic is subspaces of a vector space, again material from 4.1. So I think I'm just going to jump into the definition here. So let's suppose V is one of those abstract vector spaces that I talked about last time. So you can think about this as V could be Rn, or maybe those polynomials of degree at most 3, right? A subspace of V is a subset, let's say H of V. So a subset just means it's a sub-collection, right? Satisfying 3 things. In this case, I do want you to know the list of axioms, of properties, because they're natural, right? So the list of axioms for a vector space are a little bit, a little bit too involved, but even I can remember the list for the subspace. So the first thing is that the 0 vector, now remember, every vector space has a 0 vector, then we want it to be in H, okay? So this subcollection that you take, you better grab the 0 vector. The next one is that if U and V are in H, then when I take the sum, I want to still be in H, okay? So this is sometimes called closed under addition. If you take 2 vectors that are in H, the sum we know is going to be a vector in V because V has this addition rule, but we want it to stay in H. And then finally, if U is in H and C is any real number, then CU is in H. Okay, so let me just try to draw, before I do an example, let me try to draw just a hopefully helpful cartoon of this. You know, the way I think about this is that here's V, this vector space that this is the world that we live in, the kind of ambient world, and then H is going to be this thing here, right, this sub-collection of things. Now remember, V has this thing called the 0 vector, and we want to insist that the 0 vector is in H, okay? That's the first property here, that when I look at the subcollection, I better have that 0 vector. Part B is saying that if you take 2 vectors, I'll draw them as arrows. If you take U and V, then when I take U plus V, right, that's a new vector, and it better stay in H, right? A priori, U plus V could sit out here somewhere, and H could miss it. But, let's say that U plus, let's write it as something like this. This is like U plus V. It better stay in H, right? So my drawing is okay. And then the other condition is that when I scale U or scale V by any number, it's got to stay in there, right? So let's say this is C times U. Now, of course, in my picture, C times U can actually get outside of H, and this is, my cartoon breaks down here. But the idea is that when I scale U, I don't leave this world of H, So that's why it's sometimes, this notion is called closed under addition and scaling, because you stay in the world of H. Let me just say this is closed under addition. And part C says it's closed under scaling. Okay, so let's do a couple examples. So what's the easiest example? There's sort of 2 easy examples. I don't know if I can keep this on the same page here. Let's try to. So the maybe first example that's easiest is V is itself a subspace of V, right? So, if I happen to take the whole thing and say it's a subspace, that's allowed. And of course, the 0 vector is going to be in V because it comes with the 0 vector. And of course, if I take 2 vectors in V, their sum is still in V. And similarly, if I scale a vector in V, it stays in V. These are by definition properties that V have. Maybe a little bit more interesting, although kind of equally silly in some ways, is the 0 subspace consisting of just the 0 vector. Okay, so sometimes you can write this as the set contain the 0 vector. So let's actually go through this. So if this was, I'm going to call this H now. H is just all it has in it is the zero vector. So I've gone to this vector space and I've only picked out the zero vector and I said, okay, that thing now is a subspace. Why is that? Well, let's check the conditions, Okay, well, is the zero vector in H? Yeah, right, 0 is in H. In fact, that's all that's in H, okay? Now, what happens when I want to take two vectors in H and add them together? Well, the only thing that I can choose from H is the zero vector, and when I add it to itself, I get the zero vector, which is still in H, right? So, it's kind of silly. There's nothing to choose here from H except the zero vector. Similarly, if I take C times the zero vector, well, that's one of our axioms, actually, that the zero vector has the property that when you scale it by anything, move this up here, if I scale the zero vector by anything, I get the zero vector. This is still in H. Okay, so again, these are always going to be subspaces. No matter what V is, you get the whole thing is a subspace. And then at the other extreme, just the zero vector is a subspace. So we should look at maybe some more examples. Let me do this one here. So e.g., consider the set of vectors of the form x, y, where x is bigger than 0 and y is bigger than 0. This is a subset of the plane R2, right? Let me call this H. Okay, so what is this? This is all vectors that have, positive or non-negative, I should say, coordinates. So this is called the first quadrant, right? So I could draw this in the plane. This is all the stuff that sits over here, all these vectors here. So this is kind of H here, the first quadrant. Now let's check the conditions. Is this a subspace? Well, let's check the conditions. A, is 0 in H? So I'm asking that question. Yeah, right, because I'm allowed, what is the zero vector in the world of R2? It's the 0, 0 vector, right? So 0, 0 is in H. You're okay. So this thing contains that origin, and that means it has the zero vector. Now, is it closed under addition? Well, now it's not so easy, right? I can't just take one vector. What I have to do is take an arbitrary vector. So let's let, say, x1, y1, call this v, and x2, y2, let's call this w. Let's suppose that these are vectors in H. So what does that mean? That means that x1 is bigger than 0, y1 is bigger than 0, of course x2 is bigger than 0, and y2 is bigger than 0, right? Because I chose them to be vectors in this first quadrant. And what happens when we add them? Well, if I take v plus w, right? Well, let's see. If I take v plus w, right, the way that we add vectors is coordinate-wise. So this will be x1 plus x2, y1 plus y2. And notice now that if I'm taking the sum of two numbers, x1 is greater than 0 and x2 is greater than 0, that means that their sum is greater than 0. And similarly for the second coordinate, right? The sum of those two numbers is greater than 0. And so what I have here is a vector where the first coordinate is non-negative, the second coordinate is non-negative. This tells me that v plus w is again in H, and that's good news. That's closed under taking vector addition. But watch what happens when I start scaling now. So it looks like we're going good, right? We've satisfied the first two criteria for being a subspace, but watch what happens with the scaling now. So let me try to put this on the same page here. So for C, notice that if we let's take V to be, 2, 1, right? That's a vector that's in H. That's a legit vector in the first coordinate. It's actually something like this, maybe, this one I drew here. And if I take C to be -3, right, then what do I get? Well, then CV, the scale of this, is going to be -6, -3, and I've left this world, right? So when I scale it by -3, it goes, into the third quadrant. This is not in H. Okay, so that's bad news. It violates that third condition, so this implies that H is not a subspace of R2. Okay, So I think in discussion we'll talk about some more kind of positive examples. This is a non-example of a subspace. But yeah, I think we'll talk about some other examples or check your book for some. I want to do one more thing before we head out. Actually, another example of a positive example of a subspace. So maybe, I want to ask, how do you actually construct subspaces? And let me just do this with an example. E.g., suppose V1 and V2 are vectors in some subspace V. And let's let H be the span of all, the span of those two vectors. So as you guys know, this means that it's the set of all possible linear combinations. What I claim is that H is a subspace of V. Okay? So, this is answering the question of how do I construct a subspace? Well, one way is you take the span of, in this case, two vectors. And let me just briefly show you why this is true. I'm going to check the conditions again. So remember, if I want to check if it's a subspace, I want to know the first thing is 0 in H. Well, let's see. Can I write the 0 vector as a linear combination of V1 and V2? All right, we've seen this 100 times now that, you can always take the 0, this sort of trivial linear combination, and you get the 0 vector, okay? What happens if I take, let's say, X is a linear combination of these two vectors, and Y is a linear combination of these two vectors? So these are two vectors that are in the span. And what happens when I take the sum, x plus y? Well, this is something we've also seen in our kind of exam 1 prep. If I take the sum of these two vectors, what do I get? Well, I get c1 plus d1 times v1, right, by collecting terms. Then I get a c2 plus d2 v2. And so what do you see is that the sum of these two vectors that I chose from H is again a linear combination of v1 and v2. So this means this is still in H. That's good news, right? That the sum of two vectors in H stays in H. And finally, if X is a vector in H, meaning it's a linear combination of V1 and V2, then what is, let's say, lambda times X? Well, I'll distribute this in my head here, but it's going to be lambda C1 plus lambda C2 V2, right? So it's, again, what I see here, it's a linear combination of these two vectors, hence it's in the span of V1 and V2, it's again in H. So we've now just checked the three conditions, and this tells me that H indeed is a subspace of V. And that's a very important property. We're going to see this a lot. And let me just end with the statement that this works in general. So in fact, if let's say V1, V2, I don't have to just take 2, you can give me 1,000 vectors, let's say P vectors. If this is a collection of vectors in some vector space V, it could be polynomials or it could be R20 or whatever, then the span of those vectors, the span of V1 through VP, is always a subspace. Okay, and again, this is an important fact we're going to use over and over again as we move forward. But I think I'll end it there, and we'll talk more next time. See you then.